So, to start this afternoon, it's a pleasure to have Claus Koestler from University College Cork. And he's going to talk to us about Jones-Temperley-Lieb Algebras and the viewpoint of non-commutative.
So thank you for the invitation, and so I'm having a little short review on what I've done with many other hands together in the past 10-15 years. And so let me start here. The rough plan is that, give a little bit introduction, motivation, what it means to look at the Jones-Temperley-Lieb algebra from the viewpoint of non-commutative probability. And then we will talk a little bit about distributive invariance principles for the special case, the infinite symmetric group. And afterwards, thinking of the group algebra as well, the Temperley-Lieb algebras as a deformation of the infinite symmetric group algebra, so to see whether we can transfer what we have already obtained results for the infinite symmetric group. So let me start. So introduction, motivation. So distributional invariance principles, some of the, you know them already, but they are quite foundational in the probability theory and statistics, theoretical statistics. And essentially, they tell if one knows the joint distribution of an infinite sequence of random variables and it's invariant, yeah, this is the expectation. If it's invariant under permuting these random variables, and then this is known as exchangeability. And a weaker one, apparently, at first sight, is that if one doesn't not permute the random variables, but if one has invariance under strictly increasing maps on the natural numbers, then this is called spreadable. And now in the classical theory, classical probability theory, this is the definite theorem, and the extension looking at spreadability, that's by Ril-Narshevsky. One knows that the following three statements are equivalent. X is exchangeable, X is spreadable, and the sequence X is conditionally independent and identically distributed. Here one should note, this is the way how it's addressed by a probabilist, but this means exactly one knows everything, one can write down the model. Essentially, this is a convex combination of infinite product measures on some infinite Cartesian product of some space. And this means this is a structural, deep structural result. Just looking at the joint distributions, one can control everything. Now, so this traditional formulation one can of spreadability that we have reformulated recently with Guillaume Evans and Rolf Gomm together in 2017. And essentially what it shows that this distributional invariance principle of spreadability connects to algebraic cohomology. And so a semi-constitutional object, this means one has a functor essentially from a semi-simplicial category into probability spaces which implement a spreadability. And this is this representation here. You see the co-phase relations. Yeah, they implement essentially partial shifts. And in another way, looking at the whole situation in a more as a dynamical system, one gets unilateral Bernoulli shifts, which would be with some amalgamation, but we have a non-commutative theory for that. That's everything in a nutshell. That's why this is so important. Now, that one can go beyond definition. That's essentially this theorem here. So I have not stated that in full generality. For the purpose of this talk, it's sufficient to take W is the algebraic probability space of the following form. We have a von Neumann algebra equipped with a faithful normal tracial state, called trace. And then a spreadable sequence here is identically distributed and CS independent, come back to that in a second, over its tail algebra. And or one has also a fixed point characterization result there. The tail algebra is essentially the fixed point algebra of this partial shift monoid, which I've shown on the slide before. In the tail algebra, as usual, one takes xn plus 1, looks at the von Neumann algebra generated, and then the intersection over all these von Neumann subalgebras. And then this means essentially this commuting square independence that x, when one takes a product of x, y, and hits it, so compresses onto the tail algebra, then this factorizes in that manner. And now it's important to see that here one takes the x from that phenomenon algebra, which is generated by the xi's with some index xi, here the y from the other one with index j, and most important is that this ij are disjoint subsets of the natural numbers. And this holds true in full generality. Okay, and so this tells essentially that this commuting square independence, how we call it, is of the following: is a very strong concept. Let the phenomenon algebra M be equipped with a faithful normal tracial state. And suppose further that M0, M1, M2 are phenomenon subalgebras of M, then we say that they are commuting square independent over some subalgebra M0 if this phenomenon algebra, which is generated by M1 and M0, M2, and here we have the called M0, this forms a commuting square in the sense of Popper. There I need to emphasize, originally this was meant as a geometric condition, orthogonal pairs. But meanwhile, we have produced so many results on that that it's tempting. Yeah, it shows to be a quite strong concept. But clearly, from a probabilistic point of view, one has to say here this commuting square independence is very broad. It's without universality properties. This means the marginal distributions do not determine the joint distributions, because there one needs to have further algebraic relations one has to control from experiments. And so let me illustrate that a little bit, why we need this kind of generality and why we want it and what we can do. And we look now at distributional invariance principles for the infinite symmetric group S infinity. So it's a group of all finite permutations on the non-negative integers. And there, just to recall again, you see as usual, the infinite symmetric group is presented by the Coxeter generators, sigma 1, sigma 2, satisfying these relations. They commute when they are more than 2 apart. Where we have the typical braid relations when they are neighboring the generators in the index, and the sigma I squared is equal to E, so the usual thing. And now when we want to implement or look at the representations of the infinite symmetric group, then we have first identify a nice action of this partial shifts monoid, which we had before, which implements spreadability on the infinite symmetric group. And then that is the task of a definite theorem, characterize all extremal tracial states on the group algebra of S infinity, which are invariant under that action S. And then, in particular, one has to provide a model how to write the things down. And so this is now much more than providing an operator algebraic proof of Thomas' theorem, because then that's just a characterization of the extremal tracial states, but it does not yet provide an underlying model how one can realize them. And we have never finished pushing that to the full publication state, but a quite long preprint on that contains all the results and even results beyond that, beyond these two tasks. And just to we had been a little bit surprised at that time that this observation had not been made in the literature. So it's very easy to see if one takes a, so the point is that one has not to look at the Coxeter generators, one has to look at the star generators. So one can give a presentation of the infinite symmetric group, not in terms of the Coxeter generators, one gives that in terms of the star generators. And if one does so, this is the transposition 1 and n plus 1. If one does so, then one sees the following. If one writes down a monomial, it can come with a repetition in the star generators, then spreading them, so hitting them with a strictly increasing theta on the right-hand side, one has this kind of invariance, and that's a one-line proof, essentially. And so this means these star generators, they form a spreadable sequence, yeah? And this one here, the group algebra with the trace with respect to this character here, this is a tracial star algebraic probability space where one can pass through Kolmogorov decomposition, positive kernels, or GNS representation to get in a more operator algebraic framework. And so they are spreadable, And actually, there are even more. They're even exchangeable. Yeah. So this is a little bit. This is even true here in that case. And then, what Wolf Gohm and I could show is that this spreadable sequence is identically distributed and commuting square independent over the tail algebra of that sequence. And this tail algebra of that sequence, because it's a fixed point algebra of the action of that monoid of the strictly increasing maps, this monoid generated by them. So this is one can also think of that to be a Poisson boundary, and so one has to identify it. Yeah. And the special thing about our approach is that it's a purely operator algebraic approach. So one in the spirit of Murray and von Neumann, why they stated in rings of operators in the first paper of these four that operator or rings of operators are developed to study the representation theory of large groups. Okay, now let's just recall briefly the Thomas theorem. So the most important thing is that one has an explicit formula of hitting with an extremal character of a permutation, and one sees one has here a product. One does the disjoint cycle decomposition of this permutation, and here this mk sigma counts how many k cycles are around. And then there are non-negative numbers a1, a2, a3, and so on, b1, b2, b3, and so on. And so they are decreasing, and have to sum up to a number small equal to 1. And we gave the first operator algebraic proof of that result. Other proofs by Thoma went through totally positive sequences. Karov and Velshik, they went more through the asymptotic representation theory of symmetric groups, and Okonkov used semi-group techniques, and what he does one can find in his PhD thesis, which is also available in English. Okay. So now let's look immediately if we want to. So the question is that, can we transfer this kind of theory and the modeling to Jones-Temperley-Lieb algebras? That's the task, yeah? So here we have an explicit characterization. And let's look at this. So, and this is research in progress. So the first thing is just to recall the definition of the Jones-Temperley-Lieb algebra. So here it's good enough to look at that as a C-star algebra. There are also more algebraic approaches or parts of the theory which one can look at. So one has the EI, EJ. These are, in our context, will be orthogonal projections. They commute when they're more than 2 apart. And EI, EJ, AI, when they are neighboring, then we have this lambda AI. And lambda is essentially what has one Jones is shown. Is this the inverse of the Jones index? A very, let's say, at the moment what we are doing is that we're assuming one knows that the Jones index is discrete for when smaller equal to 4. At the moment we are assuming that to know that we are on a sound class. But of course, a fully fleshed non-commutative definite theorem would provide that this condition here, robustness of the Jones index, is part of the characterization of extremal traces on a Jones-Temperley-Lieb algebra. It has to be shown, not to be put in. So at the moment we are cheating there a little bit, but just to see how far we can get. So the first thing is that find nice representations of the partial shifts monoid S in the endomorphisms of this Jones-Temperley-Lieb algebra, and then the second class is characterize all extremal tracial states which are invariant under the action of this partial shifts monoid S. Roughly speaking, these projections E1, E2, E3, how they pop up in the fundamental construction of, let's say, one Jones. This is not the right way to look at the Jones-Temperley-Lieb algebra. For the similar reason as in infinite symmetric group, it's not the right way to look at the Cork generators. We need the other star generators. So this is now the first thing which one has to overcome the difficulty that very little is in the literature contained about other presentations of Jones-Temperley-Lieb algebra. So we have really to work from scratch, providing algebraic results. And here, this is what we have found with my PhD student this year. So suppose we have lambda t non-zero numbers which satisfy 1 over lambda is equal to 2 plus 2 plus inverse. This is the usual relation which one needs to connect the Temperley-Lieb projections to representations of the braid group. Then this Temperley-Lieb algebra, which I've just shown on the algebraic side only, is isomorphic to the unital algebra represented by the set of generators. And this is now the counterpart, yeah, of the star generators, gamma k, which are subject to counterclockwise relations. So here the counterclockwise relates to that one here. You see here you have the usual relations here, KL, K, LK, but here now, well, it's trivially true if K is equal to L, but important is that it's not only for neighboring elements, yeah, it's for any two generators have to hold this relation. This is then highly symmetric. And here comes a very specific thing. So one has this longer cycle relations, K3, K2, K1, K3, K2, K1, K2, K2. And you see here, I have done that even for Kn. One can write down longer ones, but they follow by Hopfian properties. So this means that whenever you have written down a word like that, see K3, now you see the K2, K1 comes here, K3 goes in, and then when I sandwiched that with the K2 outside. Yeah. So in the cyclic relations, cyclic stuff is going on, K3, K2, K1, K2, K1, K3. But you see here you have always, you're only allowed to rotate counterclockwise. So if you would switch K1 and K2 here in the location, that would not be true. Yeah? And but this is true in the symmetric group when you're in that context. So if when the t is equal to 1, but t unequal to 1, this is no longer true. And then one has the usual one relation here, which essentially comes from, if one would take these relations here, this would also give a Hecke algebra then, and looking at the Temperley-Lieb algebra, it's a quotient of the Hecke algebra. So here again an example for counterclockwise relations, gamma 3, gamma 2, gamma 1, gamma 3, gamma 2, gamma 1, gamma 3, gamma 2, and here this one here, but the other one where you would switch the 1 and the 2, they are not true. And how does that relate to the usual Artin generators? Yeah. So the gamma k is sigma 1, sigma 2 up to sigma k up, and then you go with, oh, there are missing inverses here, sorry for that. Sigma 2 inverse, sigma 1 minus inverse, then you go with the inverses down here. And the sigma k, this is a represented Artin generator, as usual, t times ek minus 1 minus ek. So this is quite well known in the literature. Yes? For the gamma k? Yeah. After my... After review. Yeah, so it's essentially you, after convention, so you... So essentially you have here your first strand and you pull it through in the back, and now it's always a question of the conventions. But let's take this one here. This means you have here the first, and let's say here the k plus 1, yeah, and then you braid them behind the other guys, yeah, and then the other strands run in front down. That's the one way to look at that. Roughly speaking, you don't do the presentation from that graph, yeah, where you put the sigma 1, sigma 2, sigma 3, yeah, that would be one situation here, and you do it more from a star-shaped graph that you say here's the center point, and then you have here the gamma 1, the gamma 2, the gamma 3. So this is nicely worked out by Vlacek Jesko in a quite old paper. If one presentations of the braid group associated to a planar graph. And So now here one has the spreadability. Now I just see I'm a little bit short on time, so I have to cut here, yeah. So you do the GNS representation of all these kind of things. And then let's say one looks at this generator, this we call limit 2 cycle. And this is in the context of the symmetric group. And the spectral data of this limit 2 cycle here, that is discrete, has only one accumulation point, and so this contains a double Thomas sequence. And now the conjecture, let's go down. We also know now in the context of the Temperley-Lieb algebras, we're in the robust part here. The spectrum is discrete. Now in the unit circle or unit disk in the complex numbers, only one possible accumulation point. And well, this then relates the spectrum of this contraction then relates to the Thoma double sequences, where multiplicities have to be taken care because there are no compact operators. Yeah, so this maintains this refers a little bit to Thoma measures. Okay, now the final thing what we can say here, there always go along central limit theorem. So Untitled will talk in another instance more about that as soon as one has distributional invariance principles. In that context, one always gets that. And so there exists such a probability measure, yeah. That's what we know, and now we are working on identifying that. And if we are in the setting of the infinite symmetric group representation, then we can assume even that we have a Markov trace. Then this is a bit surprising. Then the empirical distribution which one finds from that sequence going along with this gamma 1, gamma 2, gamma 3, and so on. That's the empirical distribution of a standard GOE random 2x2 matrix. So this gives a little bit of glimpse of what we are at the moment doing. So thank you for your attention.
In the interest of time, maybe we'll just move straight on. So let's thank Claus again.